population difference is not so great. And third one we said was the splitting by the adjacent protons, which actually distributes this intensity over many peaks. And that's again going to kill my intensity. And that's what I'm trying to show in this case. Take this first one, the A is a metal. And how many protons does metal have on it? 3. And therefore, what happens to that carbon? And how many peaks must it be split into? 4. So when I see 4 everywhere, I know those 4s must be because of 3 protons sitting on them. And how many of such do I have? The first one out here, which is somewhere near about 10 ppm. That's my quartet. If it's a quartet, that must mean it's a metal group. What about the one near 22 ppm? Also a quartet. It must also be a metal group. What's the next one? It's a triplet. If it's a triplet, what should that be? It should be a CH2. And what's the last one? It's a doublet. And if it's a doublet, then it must be 1 proton sitting on it. And if you look at the compound out there, the butanol that we have written out, there are 2 metals. Therefore, that explains why we see 2 quartets. There's 1 triplet that must be the CH2, the C carbon, and the doublet must be the D. And therefore, even though the splitting actually hurts my intensity and spreads the intensity over different peaks, keep in mind the splitting is giving me very useful information, because straight away it tells me how many protons are sitting on that carbon. And that's therefore useful. But very often you'll find this is not that great, because this spectrum has been obtained under conditions where the signal to noise is extremely good, meaning that they probably acquired the spectrum over a very long period of time. But you can't acquire all spectra at long periods of time, because there are people waiting to use that machine. Which therefore means you can't afford to have a split of these peaks. If you can't afford to have a split of these peaks, you must compress them. What do? Decoupling. When you do decoupling, what happens on top? You see all of them have gone away. The quartet has become a singlet, the quartet has become a singlet, triplet has become a singlet, and doublet has become a singlet, which means the intensity really picks up and you can easily differentiate it from noise. And that's basically the whole idea of doing a proton decoupling. So very often I do proton decoupling because you can't afford to have the small intensity spread out over many peaks. And that's the reason why this is done. It's fine that when you have a splitting, it gives you information, but very often I may not want that information. All I want to know is where is this carbon really processing at, where is the carbon really absorbing at. So if I know that, then I know whether it's a metal carbon, methylene carbon, a carboxylic carbon, and so on. And that's the reason why you do the proton decoupling. So this experiment essentially I put it up to show you what the effect of proton decoupling is. And this is exactly the same thing as what we spoke about in the case of ethanol, except here, while the carbon-13 spectrum is being recorded, we also shine the frequency required to make the proton transition. So the proton, if all the protons required, let us say about 350 to 400 megahertz, you shine that. The protons are making these transitions up and down, they're going back and forth, and while they're doing this transition, the carbon essentially sees only an average field used by those protons. And that's the reason why the coupling falls off. You had a question? You won't see. Because if this carbon has seen the adjacent carbon must be C13. If it is, then you will see. But that probability of C13 flanked by C13 is extremely small. I'm already having a problem seeing this one fellow. Now to expect 2 carbon, adjacent carbon atom of C13, the probability is so small that you're not going to be able to see that. Not all of them are carbon. I have so many Avogadro number of molecules, that is, some of them, that fellow is C13, some of them, this fellow is C13, and so on. But highly, the question she's asking is, why can't I see a carbon-13 split? I won't see a carbon-13 splitting, because the probability that in a given molecule, both of them are carbon-13 is 1%, right? So it's 0.01 power 2. That's going to be my probability. And that's a killer probability. You're not going to see that. And therefore, you're not going to see carbon split by another carbon split. But you'll always see a carbon split by the proton, because that's always going to happen. And that's what we're trying to decouple. take this one. Of course, here I am not showing you a coupled spectrum. I am only showing you a decoupled spectrum. And what will happen in this case? C6. Basically has 3 types of carbons in it. These two are same, these two are same, this is different. And therefore you will see 3 peaks. Of course, if I had to put carbon hydrogen coupling in it, then it would tell me how many protons are sitting on each carbon. But in this case, we didn't want to do that, we simply decoupled it, so we get extremely sharp lines and we get these information that there are 3 types of carbons. And the only way you can have 3 types of carbon, C6 and 14, is if it's a linear molecule of this type. The one thing that I would like to let you know at this point in time is in protons, we simply took the area under the peak, and the area under the peak told me how many protons there were at a given time. Why? Because just like Beer-Lambert's law, the intensity of the absorption is a direct consequence of the concentration. But even for Beer-Lambert's law, you have to understand that this is true only under certain conditions. And what are those conditions? Let's say I have 2 transitions. Molecule A makes this transition. Molecule B makes this transition. I shine light. A certain amount of intensity is absorbed by this, certain amount of intensity is absorbed by this, and we know that if there are more molecules of this type, more absorption here. Less molecules of this type, less absorption, provided the probability of absorption is the same. Let's assume that the probability of absorption is the same. In that case, how much light is absorbed here versus how much of light is absorbed here is a direct measure of how much of the compound I have in A and how much of the compound I have for B. Very straightforward, very simple. But in that, we are assuming something, we are tacitly assuming something that's quite important. And what is that? It's the following. Once the fellow absorbs, it has to come back to the ground state. If the experiment has to be sustained. Once you absorb, this fellow just stays there and doesn't come back. And what happens? Very quickly, you will have 50% here, 50% here, and then the absorption stops. We saw that. Once the population reaches 50-50, we call that saturation. If you don't want saturation, what should you do? This fellow has to come back. So once you absorb, and you know this molecule is not coming down immediately, what should you do? Do the experiment, let it absorb, shut the light off, wait for all these rays to come down. Then do the experiment again, and then see what the absorption is. If you don't do that, what's going to happen? You'll keep absorbing, after a time you'll find there is no absorption. So your experiment is actually messed up. This is something we have tacitly assumed and we have not spoken about it. That the relaxation must be quick for these guys to come back. Let us say this guy very quickly comes back, this guy does not come back very quickly. Can you now tell me that the absorption of light of this and the absorption of light of this is a direct measure of the concentration? No. Because this fellow will have no problem because it is coming back quickly. Anytime I shine light on it, the amount of light absorbed is always going to be proportional to the population, the ground state. The more molecules out here, greater absorption. And I have no problem with the population of the ground state because whatever I put upstairs is actually coming back downstairs. This fellow, I put molecules upstairs, they don't come back immediately, and therefore here I must be careful in the way I make the conclusion. I must be careful in the way I do the experiment. So what should I do in this case? I do an experiment, shut the light off, wait for the molecule to come down. Then start the experiment again. But very quickly I am going to hit saturation. Therefore, if the relaxation is not quick enough, rest assured that your intensity of absorption is not necessarily a direct measure of your population. So all these Beer-Lambert's law and everything that you have learned assumes that once you put a molecule upstairs, in the time scale of your experiment, they are all returning. If they are not returning, the relaxation is slow, then you can't assume that my absorption intensity is proportional to concentration. Because very soon you are running out of non-state population and making them equal. Now, in the case of proton NMR, the protons relax instantaneously. That's the reason why the NMR experiment is so successful. To take the proton up to plus half to a minus half spin, in no time the minus half comes back to a plus half by interacting with the surroundings. It does not happen in the case of carbon 13. The carbon 13 simply takes much longer to relax from its excited state. So if I take the carbon atom from a plus half state, put it into a minus half state, very quickly you will find that I am running out of the ground state population, because the ones that went to the minus half state are not willing to come back as quickly as the protons did. So what does that mean? It simply means that I can't take the intensity of those peaks and say that, oh, the one at 30 is bigger than the one in the middle, and therefore there are more carbon atoms there than less over here. I can't say that, because it is quite likely that the middle guy had a lot of carbons, but the relaxation was so slow that it is actually showing up to be less. So since in the case of carbon, the relaxation is not as quick as in the case of protons, unlike the protons, you cannot take the carbon 13 intensities as a measure of the carbon 13 population, of the population of that particular variety. If I had bigger intensity for the metals than the methylene protons, I can say there are more methylene protons than metal protons. But if I do the experiment with carbon and I see one peak bigger than the other, I cannot make this conclusion that the bigger peak is actually reflective of a larger number of that particular type of atom. So in carbon 13, you do not make any assumption, you do not make any conclusion with regard to the concentration or regarding the number of that particular type of carbon. All you can say is, I have a methyl carbon, I have a methylene carbon, but don't you ever talk about how many of them there are, like you would in the case of the protons. Protons, yes, you can, that's the reason why we give the integrated area and all that. You will never see a carbon 13 spectrum in which people will give you areas, because those areas mean really nothing. If I really wanted the number, what should I do? Hit the sample at a certain frequency, get the experiment going, wait for a few seconds, so they all relax, then do the next experiment. But then that would simply mean that the time I'm going to take to record a carbon 13 spectrum would be abnormally long. And that's the reason why nobody even thinks of doing that. Simply because it's an information that we probably can get from other means, and there is no way to be wasting time getting a carbon 13 spectrum which gives you intensity information, but then which probably would take you hours of operation to get that data. What I really want you to carry home as a message is that in the case of protons, the area under the peak is reflective of the number of protons of that variety. In the case of carbon 13, the peak area is not reflective of the number of carbons of that particular variety, simply because the relaxation rate for carbon is too slow, and you cannot trust that all the carbons that you put up have actually come down by the time you are ready for your next set of experiments. And that's the reason why that is the case. I'll stop here. So we have really gone through the spectra, and at 5 o'clock we'll meet again and I will do a little bit more, and whatever I do till today, 6 o'clock is what we will have for the exam. On Friday when we meet, I will discuss what I expect from you in the exam and how you sort of prepare for it. I'll also sort of summarize the whole course to tell you what is it that we went through and in what way one could actually utilize this for any of your characterization problems in chemistry. This is one that is attached to the